Thank you, and thank you all for sticking around. No matter what the venue and how excited you are to hear about things, by the end you're tired. It's just true. And I'm going to go somewhere completely different now. I want to talk about our place in the universe and how that informs the big picture of our view. And this is something that's been important through most of human history in a sort of religious sense, which I'll touch on briefly. I want to acknowledge my collaborators, Federico Lelli, a postdoc here, Jim Schaumbert, professor at University of Oregon, and Marcel Pawlowski, who was until recently a postdoc here, just moved to UC Irvine. And something that in science, it's always useful to keep in the back of your mind, because we're supposed to be skeptical of science. We're supposed to establish things, but it's easy to believe that we've learned more than we actually have. So an important bit of wisdom is that what gets us into trouble is not what we don't know. It's what we know for sure that just ain't so. That comes up a lot in life. It's worth thinking that way through, and that can happen to scientists as much as any other human. So the classic example in cosmology is the geocentric cosmology. That is, the Earth was for many centuries believed to be at the center of the universe. The sun and all the other planets, the stars, everything revolved around us. And you could build these elaborate descriptions of this. Here's the moon, here's a ring for here's the Earth, a ring for the moon, Mercury, Venus, the sun, Mars, Jupiter, Saturn, and then the stars out in the outermost ring. And there's a very specific observational reason for that ordering. That's how it has to be structured in order to explain the motions that you can see in the sky with your naked eye. Well, this is what people worked out just by going out and looking up at night before there were electric lights. Everybody saw this every night, and it made sense. So in some sense, this is the most successful worldview we ever had. This was true up until the scientific revolution. In 1543, Copernicus suggested, maybe it would work better if we put the sun at the center, had all the planets going around that, including the Earth being just now one of the planets going around the sun, and that was the dawn of what we now call the scientific revolution. That was very hard for people to wrap their head around. In fact, sometimes I go to public schools and so forth and tell kids about this. And I remember one first grade class, I said, the Earth goes around the sun. And this girl gave me this look like, what you talking about, white man? I felt abashed. No, really, yes, that's how it works, And that, if you go out, you look up, that's not what you see, right? You see the sun rise and set. It looks like the sun is going around us. You do not feel the Earth in motion the way you would if you're on a merry-go-round. It turns out because we're very tiny compared to the size of the Earth. But your intuition says that you ought to feel that motion and that you can see the sun going around us. So there's really good reason to believe in a geocentric cosmology. And it was really hard not just to suggest a new idea, and say why it was virtuous, but you also had to sort of disprove the old idea. And Galileo was one of the people who really did a lot of work on that. Now, not all of his arguments about that were correct, but many of them were, and they were ultimately persuasive, though at the time, they mostly just got him in trouble, right? Because you can have a line of evidence and show that something is wrong, and the people who like that don't want to hear that. Right. So the books by Copernicus and Galileo were officially banned by the Catholic Church until 1835 and 1824, respectively. Right. They let Copernicus out of the bag before they did Galileo. And it was only in 1992 that the Church officially exonerated Galileo, sort of a get-out-of-purgatory free card. And you can see people trying to wrap their heads around this. It's a major change to how you view the universe, how you view your place in it, and it informs your religion. So over in KSL, we have a rare books room that includes this document, which I happened to come across, and it was really fascinating. This is in 1640 text from somewhere in England. And it says here, so 1640, that's a decade after Galileo was told not to talk about this anymore, right? But the cat was sort of out of the bag and people were working it through. So that the Earth may be a planet. That is, that the body that we're standing on has the same stature of the other things that we just see as lights in the sky. And what's written here is that the seeming novelty and singularity of this opinion can be no sufficient reason to prove it erroneous. Right? Just because it seems strange isn't a good reason to discard it. Now, in a modern sense, we have a very different idea of what we think is going on. We would assert that we know, scientifically proven sense, that the sun is just one star, right? It's not just that the sun is at the center of the universe, it's the center of the solar system, all the planets go around that, but there are lots and lots and lots of stars, hundreds of billions of them just in our own Milky Way galaxy. Those are all orbiting around the center of the Milky Way galaxy, and the Milky Way galaxy itself is just one of trillions of comparably sized galaxies that are visible within the horizon. Not the entire universe, but just within the horizon we can perceive that is expanding all the time. So this image is a map of the entire sky. If you imagine building an image all the way around, up and down this way, that way, and projecting it onto 2 dimensions. And this is the whole sky. Each dot in there is one galaxy, made up of hundreds of billions of stars, and color-coded by its redshift. How fast a galaxy appears to be moving relative to us depends on how far away it is. The further away, the faster it is, because the entire universe is expanding. And people ask me what it's expanding into, so I brought a sample universe. And we have trouble wrapping our heads around the idea of 4 dimensions. Right? Einstein's general relativity, which explains this, is built in 4 dimensions, 3 spatial, 1, 2, 3, and 1 time, so that this moment comes right before, this moment comes right before, this moment. Right? So we have this linear sense of time. It doesn't have to be in general relativity, but it does have to be continuous. And so if you want to think about what the universe is expanding into, it helps to suppress one of those dimensions, because most of our brains don't work in 4 dimensions. But so what I ask you to imagine is that the surface of this balloon represents the 3-dimensional spaces, and we're just going to ignore one of those 3 dimensions. So everything we consider space is the 2 dimensions on this balloon. And that space is expanding. And so the distance between the galaxies is getting greater and greater. The galaxies themselves are not expanding. It's the space in between that's getting stretched out with time. So what dimension does the radius of this balloon represent? That's the dimension of time, right? The 3 spatial dimensions are on the surface, and the 4th dimension is the radius. So what the universe is expanding into is the future, right? The space is infinite. It's just getting more and more spread out all the time by this expansion. And the expansion is not into some other space like an explosion. It is the future of time. Of course, people also want to know what the ultimate fate of the universe is. And we don't really know that. We have speculations, but we can say more about how it began, and this whole picture emerged from a hot Big Bang, an earlier, denser place. If you run the movie backwards, everything was closer together in the past. And this is a snapshot of what the universe looked like at very, very early times. Each one of these fluctuations is a little bitty difference in temperature from this spot to that spot. When the universe was only a few 100,000 years old, it was a very uniform ball of plasma, extremely uniform in temperature, and different from what we see today, where there's lots and lots of empty space with the individual galaxies strung out along these big filaments and blobs and structures. So getting here from there, this initially very smooth condition, is hard. But gravity will do that for you. So Einstein's theory of general relativity explains why the universe is expanding. it has to in his theory. It cannot sit still. His theory does not tolerate a static universe, and he fudged it to try to make it so, because it seemed so crazy to have something that was changing. Subsequently, it was observed to be expanding, and so he's like, I should have predicted that. Should have trusted my theory, and if I had predicted it, then I would become famous. Well, he had already taken care of that part. So the theory of general relativity explains this expansion very neatly. It also gives a way of explaining the formation of large-scale structure. Gravity will make the rich go richer, so those little bitty fluctuations that start out just a tiny bit more dense attract more mass to them, and as time goes on, the gravity gets stronger, they attract more mass, it gets stronger, and so forth. And so you go from that very smooth initial condition to what you see today of a lot of empty space with galaxies embedded in it. And there's lots and lots of other data that are consistent with general relativity. But there's a dark side to this story. This story I just told you of the formation of large-scale structure works in the context of general relativity, but it needs a helping hand. It doesn't do it just with the mass that we can see. There's not enough of it. So we need, on top of normal matter, some kind of invisible substance that gives extra gravity, dark matter. And that has to be some entirely new substance, which is streaming through this room all the time, but not interacting with us other than through the very weak force of gravity. Some kind of matter that doesn't exist in our known panoply of particles and particle physics. We don't know what it is. Worse than that, the expansion of the universe is not just getting bigger and bigger all the time, but the rate of expansion is speeding up. That doesn't make sense in Einstein's theory of relativity. Gravity is an attractive force. It should be slowing down from the gravity, the mutual interaction through gravity of all the stuff inside the universe. Instead, it seems to be speeding up. And so we invoke the presence of something that basically acts like anti-gravity, but that sounds crazy. So we call it dark energy. That doesn't sound so crazy. But so the cosmology that we have now works really well. We understand that, but if and only if there is these invisible substances, dark matter and dark energy. We don't know what the dark matter is, and we don't really even understand what we mean by dark energy, other than it somehow has to drive this accelerated expansion. Now, mathematically, there are ways to do that, but it's not something intuitive. Now, I work on galaxies, nice pretty things like this, and here's the rotation curve of a galaxy. This is its speed of how stars are orbiting in this galaxy as a function of distance from the center. And you can use Einstein's, and really for this all you need is Newton's law of gravity, to work out what the rotation curve should be, given the distribution of stars and gas that you can observe. And it's that solid line. And you notice at small radius, it matches up pretty well. But as you get out to large radii, that's not true anymore. There's some extra velocity, and that's one of the reasons that we invoke the existence of this dark matter. There needs to be something giving you this extra gravity. Okay, so that's all consistent. We don't know what the dark matter is, but clearly there's something going on there. And this is something we see over and over and over again. Galaxies all have flat rotation curves. The velocity of stars is more or less constant as you go further and further out, when they should be declining because you've run out of stuff. So there needs to be more stuff. But what I noticed in doing this is that there's a tremendous amount of organization in these data. These are rotation curves for lots of galaxies now, color-coded by how concentrated or diffuse the stars are. So red is very concentrated, blue is very diffuse, and you can just see the rainbow there, right? So the rotation curve is dominated by this dark matter that we can't see, and yet it's organized by the luminous mass that we can see. So there is this controversial idea suggested by Matti Milgram, an Israeli physicist, that, well, geez, maybe what we're calling dark matter is really a failure of the equations. Maybe there's something more to it. Now, he's not saying Einstein is wrong, just saying there's something more to it than what he taught us. The equations have to be generalized. And to my shock and surprise, this theory predicted many of the things I subsequently observed. In particular, it wants all the galaxies to lie on this particular line when you plot the observed acceleration from the rotation curves against what you predict via Newton. If there were no dark matter or funny business, this would just be that straight dotted line. Instead, Milgram predicts it should be on that curved line. And so what you'll see here is a 1 minute long movie of all these 150 galaxies that we've been working on. Here's the rotation curve of the individual ones, the actual observed data. The blue line is how much contribution you get from the stuff you can see. And then on this side, what the actual acceleration is versus what the predicted acceleration is, applying Newton's laws to the stuff you can see. And there's a one-to-one correlation. How much stuff you see is predictive of what you get for the acceleration. That is exactly what Milgram predicted, and it's the one thing that really should not happen in this theory of dark matter. Dark matter should be calling the shots. We don't care what the baryons are doing, the normal matter, and yet there's this one-to-one correlation. And so it may be that what we're calling dark matter, and confidently asserting that we understand how the universe works, maybe this is just a proxy, as in olden days, for something that we don't understand. Right, so I see some logical options that dark matter is fine, don't worry about it. I hear that from lots of my colleagues. We're sure it's right, it'll all work out. I'm not so sanguine. The other option is, according to the scientific principle, if a theory makes a prediction, maybe that's because there's something to it. But that has this implication that the dark matter we need for other reasons doesn't exist. So I think we still have a lot to learn. That's great. Even though we've made a lot of progress, we're not at the end of science. It's not like we're just filling in the last decimal points. There are still fundamental things to be learned, and that should be something that's inspiring to everyone. There are still things you can do that are new and unique in this world. So thank you all for attending and for listening to me.